Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to discuss what are called Partially Observable MDPs, or POMDPs. The term partially observable should be pretty intuitive. Basically, it means your state doesn't have full information about the environment, which is something we already know. So in fact, a POMDP is a more realistic model. To get a better intuition about this, think about how you would describe the state of the room you are in. To do this, you would probably turn your head and look around. While you look around, you will probably keep track of what you saw and compile that information in your mind. So similar to what we did with regular DeepQ learning, we combine observations to give us a more accurate depiction of the state we're actually in. The key concept here is, if what you see at a particular time doesn't give you full information about a state, then you can combine things you see at other times too, to give you more information. In other words, we combine observations across time. In deep learning, this would be considered a sequence of observations. We know that the way we deal with sequences in deep learning is with recurrent neural networks. By using a recurrent neural network to approximate either the action value function Q or the policy, we can make a function approximator that depends on previous states as well as the current state. Computationally, doing DeepQ learning with recurrent neural networks is hard. One complication stems from the fact that what we usually do is randomly sample from the experience replay buffer. However, if we take a random sample, then the states won't be ordered, and we won't be able to feed a proper sequence of states into the recurrent network. Let's discuss some possible solutions to this. First, we can continue to use the experience replay buffer as we have already. In other words, each item in the experience replay buffer is a sequence of 4 observations. Then, instead of concatenating the 4 observations into one image with 4 colors, we can consider it a sequence of 4 black and white images. The downside to this is the sequences will be limited in length. You could, however, use a longer sequence, like 5, 6, 7, or 8. While this limits the sequences to always being the same size, this is actually easier implementation-wise. Another thing you can do is just sample randomly from the experience replay buffer, but then don't use those samples as indexes to states, but rather use them as indexes of end states. So for example, suppose I randomly pick index 300 and I want to consider sequences of length 10. Then what I do is feed in all the states from index 290 up to 300 into the recurrent neural network. In this situation too, it is more convenient to use sequences of constant length. One advantage of this method is that you don't need to store 4 separate images as part of each state, but rather just one. So in effect, that saves memory. Remember that in regular DeepQ learning, the state has redundant information. State S of t contains the images x of t minus 1, x of t minus 2, and x of t minus 3. But state S of t minus 1 already contains x of t minus 1, x of t minus 2, x of t minus 3, and x of t minus 4. However, this redundancy makes things easier to implement during training. Another thing to think about is that if you consider each state to be just a single frame, and you continuously append these to your experience replay buffer, you can't naively just always search 10 frames behind to find the beginning of a sequence. Why might that be? Well, if we choose the 5th frame of an episode, let's say, then it doesn't have 10 previous frames, so we can't go back that far. So you also need some way to keep track of episode boundaries if you're going to use this method.